So we'll be studying principles and techniques of biochemistry and molecular biology. 7th edition by Keith Wilson and John Walker. Why? Because we have not yet started. I have not yet started to study. So I'll just start with this book. So let's see the index of this book. What is happening? Basic principles. It's about 30 pages. Cell culture and techniques, 30 pages. Centrifugation, 20 pages. Microscopy, important chapter, 30 pages. Molecular biology, bioinformatics and basic techniques, 50 pages. We have PCR here, gene and nucleotide sequencing and of DNA here, recombinant DNA and genetic analysis, 60 pages. Okay, immunochemical techniques, it is very important, and it is about 30 pages. Protein structure and purification, characterization and function analysis, 50 pages, about 50 pages. Mass spectrometric techniques, about 40 pages. Electrophoric techniques, about 30 pages. Chromatographic techniques, about 40 pages. Spectroscopic techniques, about 30 pages. Spectroscopic techniques part 2, 30 pages more. Reduced isotope techniques, 30 pages. Enzymes, 40 pages. Principles of clinical biochemistry, 30 pages. Cell membrane receptors and cell signaling, 40 pages. Drug discovery and development, 30 pages. We'll be studying about one or 1.5 chapter every day. So I hope we'll complete this whole book in half a month or in a month, because I procrastinate a lot, right? So there is this introduction thing. There are these abbreviations: AMP, adenosine monophosphate. This is the first time I am seeing somebody writing 5 here, 5 in these places. So maybe if in exam an abbreviation comes, I'll be writing this: adenosine 5 monophosphate, ADP, adenosine 5 diphosphate, ATP, adenosine triphosphate, BP are base pairs, CAMP is cyclic AMP, adenosine 5 monophosphate. CHAPS, CHAPS, it is 3 chloroamidopropyl dimethyl amino 1 propane sulfonic acid. This is a big molecule. CHAPS, CHAPS. 3,3-chloroamidopropyl dimethyl amino 1 propane sulfonic acid. Quite a mouthful. Okay, CMP, counts per minute. CTP, cytidine triphosphate. Only this is replaced by A and it becomes ATP. Okay, cytidine triphosphate. Now I want to know why there is not 5 here. DDT, 2,2-bis P chlorophenyl 1,1,1 trichloroethene. Okay, good. 2,2-bis P chlorophenyl 1,1,1 trichloroethene. There will be a day when I'll remember its structure. It is an ethane, so CCC trichloroethane. So it is 1,1,1 trichloroethane, Cl, and a Cl. If this one I take it as 1. Now it is 2,2-bis chlorophenyl. So it will be 2,2 because this one I am taking is 2,2. Okay, chlorophenyl, there is a chloro and a phenyl. I don't remember the phenyl. Okay, it will be maybe like a benzene group. Benzene group like this, and para, ortho meta para. This is para. Don't trust me, but I think this is DDT according to what this says. 2,2 bis p chlorophenyl, if this is a chlorophenyl, okay, and 111 chloroethane, trichloroethane. Okay, I don't believe myself. Let's Google it. Shall we? Shall we? Shall we Google it? Shall we Google it? No, we will not. Haha. No, we will Google it. DDT. Go. Structure. So it looks like this. Okay. Do you see where I went wrong? I do. It was propane. I don't understand. Once again, Google. Methane, ethane, propane, butane. So this one was propane. There should be 3 carbons. Okay. Why are there no 3 carbons? Why is this like this? Why is there a shortage of carbon? Oh god. See, here it is written ethane. Ethane. Okay, so my knowledge in organic chemistry is not wrong. I was reading wrong. Oh my goodness. It is written ethane here. I am little blind. I am very sorry. Why was I looking at that? Why was looking at chat? So it will go like this. Okay. Now I will remember DDT. DMSO, dimethyl sulfoxide, DNA, deoxyribonucleic acid, E electron, EDTA, ethylene diamine aminotetracetate, ELISA, enzyme linked immunosorbate assay, FAD, phenyladenine dinucleotide, this is oxidized, FADH2, flavin adenine dinucleotide reduced, FMN, flavin mononucleotide, flavin adenine dinucleotide, this is reduced, flavin mononucleotide oxidized, flavin mononucleotide reduced. GC, gas chromatography, GTP, guanosine triphosphate. Why is this there no 5' here? HAT, hypoxanthine aminopterin thymidine medium. I don't understand this. HIPS, 4,2-hydroxyethyl 1-pipazine ethane sulfonic acid, HPLC, high performance liquid chromatography, KB, kilobase per pairs. MR, relative, okay, this is new one. MR, relative molecular mass. Min is minute, NAD plus nicotinamide adenine dinucleotide oxidized, nicotinamide amide dinucleotide reduced, nicotinamide adenine dinucleotide phosphate oxidized, nicotinamide adenine diphosphate reduced. Pipes, it just reminded me of Harry Potter. The basilisk roams through the pipes. What are the pipes? 1,4 pipe resin bis ethane sulfonic acid. This is so complicated. PI inorganic phosphate, ppm parts per million, ppb parts per billion, ppi inorganic pyrophosphate, RNA ribonucleic acid, RPM revolutions per minute, SDS sodium dodecyl sulfate, sodium dodecyl sulfate. Tris. Why is tris just tris? But it is just tris. It is 2 amino 2 hydroxy methyl propane 1,3 diol. Okay, so we'll start with the basic principles. It has quite a bit of pages here, so we'll be reading about biochemical molecular biology studies, units measurement, weak electrolytes, quantitative biochemical measurements, safety in laboratory, suggestions for further reading. Will we take these suggestions? Will I take these suggestions or not? We'll see in the future. So I was trying to read it on my own, and then it was unsuccessful because I cannot study on my own. I need to blabber it out and for someone to hear it. And now this someone is you guys who opted to watch this video. Okay, it's your fault, not my fault. Biochemical and molecular biology studies, aims of laboratory investigation. So, what are the aims of laboratory investigation in biochemistry? The study of chemical processes that occur in living organisms with ultimate. Okay, what do we study? We study the chemical processes that are occurring in living organisms with the ultimate aim to understand the nature of life in molecular terms. Okay, the biochemical studies relies on the availability of appropriate analytical tools. It will only happen when there are appropriate analytical tools available, and the applications of these techniques to the advancement of the knowledge of the nature. So there are tools present or not present, then only we'll be studying. And then the application. So application, not anyhow, we need to use these techniques for the advancement of the knowledge of nature. What kind of knowledge? What is the nature, okay, of the subject we are studying? The relationship between A's relationship between B, and the biological molecules. What kind of biological molecules these are? The proteins, the nucleic acid, and what are its cellular function? In recent years, huge advances have been made in our understanding of gene structure and expression in the application of the techniques such as mass spectrometry to study the protein structure. So, what is mass spectrometry used? To study the protein structure and function. Human genome project in particular has been the stimulus for major developments in our understanding of many human diseases, especially cancer, and for identification of strategies that might be used to combat these diseases. The discipline of molecular biology overlaps with the biochemistry, and in many respects the aim of the two disciplines complement each other. Okay. Molecular biology is focused on the molecular understanding of the process of replication, transcription, and translation of genetic material, whereas biochemistry exploits the techniques and findings of molecular biology to advance the understanding of such cellular processes as cell signaling and apoptosis. So we'll underline this because we need to remember this. Molecular biology is focused on the molecular understanding of processes of replication, transcription, and translations of genetic material, whereas biochemistry exploits the techniques and findings of molecular biology to advance our understanding of such cellular processes as cell signaling, apoptosis, and apoptosis. The result of that two disciplines now have the opportunity to address issues such as, so they are the structure and function of total protein components of the cell. We can now understand whatever the issues that have in the structure and function of total protein components of cell. So it is proteomics. What is proteomics? The understanding the structure and function of total protein component of cell and of all small molecules of the cell. Meta Metabolomics, whatever is happening inside whatever small molecules are inside the cell, we'll go for metabolics. For proteins, we'll go for proteomics. The mechanisms involving in the mechanisms involved in control of gene expression, whatever happening, what are the mechanisms that are involved in gene expression. Okay, identification of genes associated with wide range human diseases, very important. Whatever genes are associated with human diseases. Development of gene therapy strategies for treatment of human diseases. The characterization of large number of orphan receptors whose physiological role and nature and natural diagnostic are currently unknown, present in the human genome, and their exploitation for the development of new therapeutic agents. We don't know a lot. The identification of novel disease specific markers for the improvement of clinical diagnosis. Why am I having a slip of tongue? The engineering of cells, wow, especially stem cells to treat human diseases. Okay, the understanding and functioning of immune system in order to develop strategies for protection against invading pathogens. The development of our knowledge of the molecular biology of plants in order to engineer crops improvements, pathogen resistance and stress tolerance. Very nice. The application of biomolecular techniques or to the nature and treatment of bacterial, fungal and viral disease. The remaining chapters in this book will address the major experimental strategies and analytical techniques that are routinely used to address issues such as these. Okay. So experimental design. Advanced biochemistry and molecular biology, as in all sciences, are based on the careful design, execution, and data analysis of experiments designed to address specific questions or hypotheses. Such experimental design involved a discrete number of compulsory stages. Number one, the identification of subject for experimental investigation. The identification of subject for experimental investigation. Okay, the critical evaluation of the current state of knowledge for the chosen subject area, nothing that noting the strengths and weakness of the methodologies previously applied and the new hypotheses which emerged from the studies. The formulation of the questions or hypothesis to be addressed in plain experiment. The careful selection of the biological system, species in vitro or in vivo to be used for the study. The identification of the variable that is used to study. The consideration of the other variables that will need to be controlled so that the selected variable is the only factor that will determine the experimental outcome. Okay. The design of the experiment, including the statistical analysis of the result, careful evaluation of the material and apparatus to be used, and the consequential potential safety aspects of the study. The execution of the experiment, including appropriate calibrations and control, with a careful written record of the outcomes. The replication of the experiment as necessary for the unambiguous analysis of the outcome. Okay. The evaluation of the outcomes, including the application of the appropriate statistical test to quantitative data where applicable. The formulation of the main conclusion that can be drawn from the results. the formulation of new hypothesis of the future experiment that emerged from the study. The results of the well-designed and analyzed studies are finally published in the scientific literature after being subject to independent peer review. And one of the major challenges facing professional biochemists and molecular biologists is to keep abreast of the current advances in the literature. That is so true. Fortunately, the advent of the web has made access to the literature easier than it once was. Very nice. So now we'll be understanding the units of measurement, or the SI units. The French system international, the unites. The units. The SI unit is accepted convention for all measurements in all units of measurement. Basically, table 2.1 lists the basic and derived SI units. Table 1.2 lists the numerical values from some physical constants in SI unit. Table 1.3 lists the commonly used prefixes associated with quantitative terms. Table 1.4 gives the interconversion of non-SI units of volume. Important thing that we'll be mostly seeing in while doing an experiment is use of molarity. This thing called morality and this thing called molarity. It's very different. So in practical terms, 1 mole of a substance is equal to the molecular mass. One mole of a substance is equal to its molecular mass expressed in grams. Is equal to molecular mass in grams. It's a weird way of saying it, but okay, I'll go for it. So now then, where the molecular mass is the sum of the atomic masses of the constituent atoms, so that the term molecular mass is preferred to the older term molecular weight. The SI unit of the concentration expressed in the terms of moles per cubic meter. Moles per cubic meter. This is good one. The SI unit of concentration expression in terms moles per cubic meters. In practice, this is far too large for a normal laboratory. Of course, we cannot use cubic meters. Oh my god! And based on the cubic decimeters. Okay, so we'll be using this as preferred. However, some textbooks and journals, especially those of Northern American origin, tend to use the older unit of volume, namely the liters and its subunits. So basically, what we know is 1 dm cube, or 10 raised to minus 3 meters, is equal to 1 liters. However, okay, rather than the cubic centimeter. In this book, volumes will be expressed in cubic decimeters or its smaller counterparts. The molarity of a solution of a substance is expressed in the number of moles on a substance in 1 cubic decimeter of solution. It's expressed with the symbol M. So molarity is equal to number of moles in 1 cubic decimeter. 1 cubic decimeters. I don't understand. What is this saying? Because from what I know, this is this upon volume, whatever volume it is, and then we'll multiply this with this 1000 to keep it in meter cube normally. Okay, and then this goes for given mass upon molecular mass, so gm upon mm into v upon 1000, but it will be kept in liters or m cube. So for this person, so this is 1 molar, 1 millimolar, because so it will be what, multiplied by 1000 or divided by 1000. Anyways, let's move on. So it should be noted that the atomic and molecular masses are both expressed in daltons or kilodaltons. Okay. What happened to U? Who knows? 1 dalton is an atomic. There was this AMU which changed to U. Okay. 1 dalton is the atomic mass unit, equal to 1/12 of the mass of the one atom of carbon 12 isotope. However, biochemists prefer the term relative molecular mass. It is defined as the molecular mass of the substance to 1/12 of the atomic mass of the carbon 12 isotope. M therefore has no units. MR therefore has no units. Thus, the relative molecular mass of sodium chloride is 23 sodium plus sodium chloride, and 30.5 for chlorine. It's 58.5. So that 1 mole is this. Let us check out the table. So length in meters, mass in kilograms, time in seconds, electric current in amperes, temperature in Kelvin, luminous intensity in candela, CD, amount of substance in mole, derived units. So force in newtons. Force, what is force? Mass upon area. F is equal to ma, mass into acceleration. Okay, I am becoming dumb day by day. So this is mass and this is acceleration, if you see it right. So okay, I don't know what is this equivalent SI unit, so we'll be moving on. Energy, work and heat are in joules, power, radiant flux in watt, electric charge in quantity in coulomb, electric potential difference ampere into volt is V, electric resistance is ohm, pressure is Pascal, frequency is Hertz, magnetic flux is Tesla, area is meter square, volume is meter cube, density is kilogram per meter cube, concentration is mole per cubic meter. Avogadro constant is Na, 6.022 into 10 raised to the power 23 moles, mole inverse. Okay, I will remember this. Faraday is a constant, 9.648 into 10 raised to the power 4 coulomb per mole. Planck constant H, 6.626 into 10 raised to the power 34 Js, joules second. Universal and molar constant R, this is a very important person, 8.314 J K inverse, mole inverse. Molecular volume of an ideal gas, 22.41 dm cube, mole inverse. Velocity of light in vacuum is C, 2.997 into 10 raised to power 8 meter per second. Energy, calories 4.184 joules. Erg, 10 raised to power minus 7 joules. Electron volt EV is 1.602 into 10 raised to power minus 19 joules. Pressure in atmosphere 101,325 Pascal bar 10 raised to power 5. We also take this equal to 10 raised to power 5. Okay, millimeter of mercury, mmHg, 133.322 pascals. Centigrade, degree centigrade. Temperature in centigrade plus 273.15 to convert it into Kelvin. Fahrenheit, temperature degree Fahrenheit minus 32 into 5 by 9, so 5 by 9 plus 273.15. Sorry, this portion is what it will convert it into centigrade, and then it will be, we will add this to make it into Kelvin. Angstrom, this is angstrom, is equal to 10 raised to power minus 10 meters. Inch is this. Mass in pounds, this is pounds, this much is pounds. Okay, whatever. If this was dissolved in water adjacent to total volume of this, the solution would be 1 molar. What is this saying? 1 mole NaCl is equal to 58.5 grams. Is dissolved in water and adjusted to total volume is equal to 1 dm cubed. The solution would be 1 molar. The solution would be 1 molar. The biological substances are most frequently found in the relatively low concentration and in vitro model systems. The volume of stock solution regularly used for experimental purpose are also small. The consequences of this experimental solutions are used in millimolar, micromolar, nanomolar range, then molar. Table 1.5 shows the interconversion of these units. This is table 1.3, common prefixes associated with the quantitative terms. 10 raised to power 24, whatever, read it yourself. I don't want to read this. Okay, interconversion of SI, non-SI units and SI units. This is liter, milliliter, microliter, nanoliter. Damn. Okay, interconversion of millimolar, micromolar, nanomolar, whatever, molar, millimolar, micromolar, nanomolar. So now next portion is weak electrolytes. So the biochemical importance of weak electrolytes. Many molecules of biochemical importance are weak electrolytes, and in that they are acids or bases that are partially ionized in aqueous solution. Example include the amino acids, peptides, proteins, nucleotides and nucleic acid. It also includes the reagents used in the preparation of buffers such as ethanoic, acetic acid and phosphoric acid. The biochemical function of many of these molecules is dependent upon their precise state of ionization at prevailing cellular or extracellular pH. Okay, the function depends on the pH level of cellular or extracellular wherever they are present, on the precise state of ionization. Catalytic sites of enzymes, for example, containing functional carboxylic and amino groups from the side chains of the constituent amino acids in the protein chain, which needs to be specific ionized state to enable the catalytic function of the enzyme to be realized. Therefore, before ionization of these compounds is discussed in details, it is necessary to appreciate the importance of the ionization of water. So let us see the ionization of weak acids and base. One of the most important weak electrolytes is water. Since it ionizes to small extents to give hydrogen ions and hydroxyl ions, this is hydrogen ion, this is hydroxyl ion. In fact, there is no such species as free hydrogen ion in aqueous solution as it reacts with water to give hydronium ion. Well, as it says, there is no such species as free hydrogen ion, so it will react with water again to give us hydronium ions. Even though free hydrogen ions do not exist, it is conventional to refer them as the hydronium ions. Okay. The equilibrium constant of the ionization of water has a value of 1.8 into 10 raised to power 16 at 24 degrees Celsius. It is called Celsius or centigrade. Now I am confused. Dear English, be a good person. Okay, so how do we find the ionization? So first of all, we will take this equation. Okay, and K equilibrium of this equation is the concentration of products divided by concentration of reactant, and it has come to be around 1.8 into 10 raised to power 16 what? No what? Concentration upon concentration has no units. The molarity of pure water is 55.6. It can be incorporated to a new constant of Kw. So we are multiplying K equilibrium into molarity to give Kw. Okay. Kw is known as autoprotolysis constant. Autoprotolysis constant. This is a new one of water and does not include. So what is this equals to 1 into 10 raised to power minus 14 is equal to Kw. Okay, this is nice, and does not include the expression of concentration of water. Its numerical value is exactly 10 raised to power minus 14 related to specifically at 24 degrees Celsius. At 0 degrees Celsius, Kw has a value of 1.14 into 10 raised to power 15, and at 100 degrees Celsius a value of 5.45 into 10 raised to power 13. The stoichiometry in the equation 1.2 shows that the hydrogen ions and the hydroxyl ion produce in 1:1 ratio. Hence, both of them must be present at the concentration of this. Since the Saueressian definition of pH is that it is equal to the negative logarithm of the hydrogen ion concentration, it follows the pH of pure water is 7. So this is the definition of neutrality. Ionization of carboxylic acids and amines. So we saw the ionization of water. Now we'll see carboxylic acids and amines. Carboxylic acids and amines. Previously stressed about many biochemicals, important compounds contain a carboxyl and a primary, secondary and tertiary. RNH2, R2NH or R3N amines which can donate or accept hydrogen ion on ionization. So it will become COO minus or COOH2 plus. This will become RNH3 minus or RNH2 plus, I think so, something like that. Okay, the tendency of the weak acid, generally represented by Ha to ionize, is expressed by the equilibrium reaction of this Ha, equilibrium sign H, which is taken out, plus A conjugate base, anion, whatever is left. The reversible reaction can be represented in the equilibrium Ka, known as the dissociation constant. Equation is this. Ka is equal to H plus A minus upon HA. Note that ionization of the weak acids results in a release of hydrogen ion. Okay, whenever there is an ionization of weak acid, the hydrogen ion is released and the conjugate base of the acid, both are ionic in nature. Similarly, amino groups, primary, secondary and tertiary, as weak bases can exist in ionized and unionized form, and the concomitant ionization process is represented by the equilibrium constant Kb. Okay, RnH2 plus H2O will give RnH3 plus, I was saying that, plus OH minus. Okay, so this one loses and this one gains. So we'll be getting this. In case of non-ionized form of base, abstract hydrogen ion from water to produce a conjugate acid that is ionized. If the equation is viewed from the reverse direction, it is similar to that of format of equation 1.3. Equally, equation 1.3 viewed in reverse similar to the format of 1.4. A specific and simple example of the ionization of weak acids is that of acetic acid, ethanoic acid. CH3COOH is taken and it will lose an H, so it becomes this. Acetic acid and the conjugate base, acetic acid and acetate ion, the acid, acetic acid and the conjugate base, acetic ion, acetate ion. This is the conjugate base, known as conjugate acid pair. The acidation constant can be written as follows: Ka. Okay, this K has the value of this. In practices of this for common expressed in the terms of the negative algorithm, it refers to as pKa. Thus, in case of pKa is equal to this, it can be confirmed from the equation numerically. pH is 50% of acid and is protonated and ionized and 50% deprotonated. It is possible to write the expression of Kb in the acetate ion as conjugate base. This is the Kb. So in this, we are taking acetate base plus water. We'll get acetic acid because H is added and OH is released. So we'll be getting weak acetic acid, weak acid, conjugate base is here, water is here. We do not take water in this concentration game. Okay, so its value is this. Multiplying this, we'll get this. So we'll know that Ka into Kb equals to the concentrations of H plus and HO minus, because everything else cancels out. Okay, this and this cancels out with this and this, so we'll be getting this and this multiplying, we'll get this. Acetic acid, pKa is 4.75, butyric acid 3.98, and other tris A is 8.41. What kind of acid is this? Okay, it's a base. Pipes is 6.8. Wow. So let's see the most lethal one. Oh, phosphoric acid, weird acid. Okay, pKa plus pKb is pKw, that is equal to 14. This relationship holds of all the acid-base pairs enables one pKa value to be calculated from the knowledge of the other. Biologically important examples of the conjugate acid-base pairs are lactic acid, lactate, pyruvic acid, pyruvate, carbonic acid, bicarbonate, and ammonia. In case of ionization of weak bases, the most common convention is to code the pKa, the Ka or the pKa of the conjugate acid rather than the Kb or pKb. for the weak convention we are talking about. Example, pKa value of some weak acids or base are given in the table, and smaller numerical value of pKa is stronger acid or ionized, the weaker is base. Weak conjugate weak acids can be predominant unionized in the low pH value. Whatever, I'm not reading more. This sensitivity to pH of the state of ionization of weak electrolytes is important both physiologically and in vitro biochemical studies, employing such analytical techniques as electrophoresis and ion exchange chromatography. Weak acids will be predominantly unionized at low pH values and ionized at high pH values. Okay. In constant contrast, weak bases will be predominantly ionized at low pH value and unionized at high pH value. This sensitivity to pH of state of ionization of weak electrolytes is important to both physiologically and in vitro biochemical studies, employing such analytical techniques such as electrophoresis and ion exchange chromatography. Ionization of polyprotic weak acids and base. So we have some polyprotic weak acids and bases are capable of donating and accepting more than one hydrogen ion they are accepting. Each ionization stage can be represented by a Ka value using the convention that Ka1 refers to the acid that is more ionizable atoms, and Kan the acid with the least number of ionizable hydrogen atoms. Okay, one of the most important chemical examples of is phosphoric acid H3PO4, as it is widely used as the base buffer in pH region of 6.7. See the table below. So we see here where it has 3 gives and 2 is still left. Now it has 2, it gives 1 and 1 is still left. It has 1, it gives 1 and 0 are left. So higher the number of hydrogen atoms it has to give, its pH is the lowest. Okay, it's more acidic. Okay, the lower it has the H ions, H plus ions to give, the higher is the pH. Basic it is. Calculation of pH and the extent of ionization of liquid. Calculate the pH of 0.01 molar solution of acetic acid and its functional ionization given that its Ka is 1.75 into 10 raised to the power 5. So basically concentration of acetic acid is given CH3COOH, concentration is equal to 0.01. okay, Ka is 1.75 into 10 raised to power minus 5, and its functional ionization, calculate the pH. They want to know the pH. So how does one find the pH? Let us see. So we'll use this formula first, because Ka is equal to this and the concentrations are used here. Since acetate and hydrogen ions are produced in equal quantities, the X is equal, if X is equal to the concentration of each, then the concentration of the unionized remaining will be this total minus X. That's true, because CH3COOH is equal to CH3COO minus plus H plus. So if this is 0.01 and this is 0.0, so now after some times it will remain X, but it will become 0.01 minus X. right? Or vice versa. 0.01 minus x, it will become x and x. So these are the new concentrations. So we'll use this formula: acetate x upon 0.01 minus x is equal to 1.75 into 10 raised to power 5 minus 5. It is the majority of the acetic acid present in a nice form. If the pH is increased, this blah 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 blah. Oh god, this is a heavy chapter. I did not know how heavy it will be. It's already been about an hour and we have just reached 1.13 buffer solutions. Buffer solution was the one that resists a change. It resists a change in pH. Important on the addition of either acids or bases. They are anomalous. What is biochemical work? As so many biochemical molecules are weak electrolytes, so that their ionic status varies in pH with pH. So this is a need to stabilize the ionic status. What are the same? So in biochemical works, they are weak electrolytes and they change their ionic values with pH. So to stabilize this ionic status during the course of practical experiment, a buffer is used. Buffer resists the change in pH. In practice, buffer solution consists of aqueous mixture of a weak acid and its conjugate base. The conjugate base component would neutralize any hydrogen ion generated during the experiment, whilst the unionized acid would neutralize any base generated. The Henderson-Hasselbalch equation of central importance in the preparation of buffer solution. It can be expressed in the variety of forms for a buffer based on the weak acid. So pH is equal to pKa log plus log conjugate base upon weak acid, or pH is equal to log an ionized form upon ionized form for a buffer of conjugate acid of a weak base is this or this. In table there are some weak acids and bases commonly used in preparation of buffer solution. Phosphate, Hapes, pipes are commonly used in the optimum pH of 7.4. The buffer action and pH of blood is illustrated in example 2 and the preparation of phosphate buffer given in example 3. Buffer capacity. It can be seen from the Hazen-Hazelbuch equation that when the concentration of a weak acid and base is equal, the ratio of one of their logarithm 0, so that the pH is equal to pKa. The ability of the buffer solution to resist a change in the pH of the addition of strong acids or alkali is expressed by its buffer capacity. It is defined as the amount of moles of acids or base required. Okay, beta is equal to dB upon dpH is equal to minus dA upon dpH, where dB and dA are the amount of base and acids respectively, and dpH is the resulting change in pH. In practice, beta is the largest when pH range within pH range pK is plus minus 1. Normal pH of blood is 7.4 and is maintained at this value by buffer action, in particular action of CH3 minus and CO2 resulting from gaseous carbon dioxide dissolved in blood and the resulting ionization of carbonic acid. So CO2 plus H2O gives H2CO3. H2CO3 gives H plus and HCO3 minus. If possible, to calculate an overall equilibrium constant K equilibrium for the two consecutive reaction to incorporate the concentration of pH 55.6 molar in the value. Let us see. So K equilibrium is ions concentration of H ions and this concentration and carbon dioxide concentration. We get this. Hence the P equilibrium is 6.1. So pH when we find out is P equilibrium plus log of this concentrations. When pH of blood fails due to the metabolic production of, I like this, it is making me understand quite many things right now. When due to the production of H plus, when H plus increases, this will also increase, so this will also increase, so this will also increase. The shift in favor of increased production of H2CO3, that in turn ionizes and gives carbon dioxide that is then expired. When the pH of blood rises, more HCO3 is produced and breathing is adjusted to retain the carbon dioxide. These diseases takes many changes in this pH cause either acidosis or alkalosis. This causes serious problems in extreme cases. For example, obstructive lung disease may cause acidosis and hyperventilation, alkalosis. Clinical biochemists routinely monitor patients' acid-base balance in blood. In particular, the ratio of HCO3 minus and CO2. Reference ranges for these: pH 7.4 are CO3 minus, HCO3 minus is equal to this. Okay. So the question is, a patient is suffering from acidosis. If it is an acidosis, then there is seen an increase in either H plus or HCO3 plus, minus. Okay, so now we are seeing it, and has a pH of 7.15. Normal it is 7.4. 7.4. Okay, so if it is an acidosis, so the pH will decrease. So pH will decrease, that means CO2 level has been increased. So for this, the carbon dioxide is 1.15 mm. Normal range is 1.2. What was the patient's HCO3 negative? What is the implication of this value? So we'll take this formula. We'll put 7. T equilibrium is 6.10. This is constant. Why? Okay, anyways, so it is 6.10. Okay, then it is a given value, we need to find this value. Okay, so this is been subtracted here, we got this log of this, then taking the anti-log of the equation, we get this. Now we'll multiply this to this. Therefore this is the concentration we found out of HCO3. Normal should be about from this to this. Okay, and PCO2 should be about this. And what was found? This. So sad. Let me check one thing. 4.6 plus 6.9, 6 is at 9, 15, 10, 11 upon 2 equals 5, 1, 5, 7, 1, 2, 5. Okay, it is not an average. This is a random number taken or something, because I am not understanding this. There's another question and there is selection. Okay, we'll do later chapter later, because I'm tired and I need dinner. Okay, part 2 will come one day. Bye bye.